I will present some results of a recently finished project called iNano, which actually involves results from 2 different XIDE projects. So first, I would wait a minute. Why is it not moving? Okay, I hope it. Okay, now it's working. Sorry. So first, let's talk a little bit about the iron cycle. So iron is an essential micronutrient for oceanic primary producers. However, the sources of iron, especially in the ocean, are very limited and often associated to the continents. So we have the input via the rivers or via atmospheric dust. And this leads to the fact that actually vast areas in the ocean are depleted in iron. And here on the map, I would like you to focus on all the circles that have orange either in the center or at the rim, which marks areas where iron is the primary or serial limited nutrient for oceanic phytoplankton. And oceanic phytoplankton is a major component of the carbon pump. So this is actually what absorbs the CO2 from the atmosphere. And when they're dying, it's settling down into the deep sea and stores the carbon in the sediments. So this is why I was very excited when it was discovered that hydrothermal vent systems can contribute significant amounts of iron into this otherwise depleted environment. And right now, we are assuming that around 11 to 22% of the dissolved iron in the deep sea. I'm hearing someone, I don't know who is, okay, in the deep sea is actually sourced from hydrothermal vent systems. But we don't really fully understand how this transport process works, how we can transport the iron from the actually source, the hydrothermal vent systems, into the deep sea, especially the reduced iron, the iron 2, which is more soluble and more bioavailable. And right now there are 2 main theories. And the first one is the organic complexation, so that the iron forms complexes with organic matter, which stabilizes it and allows the transport into the deep sea. The second theory is the inorganic mineralization. So it's a complete inorganic process, which keeps the iron in the colloidal size frame and allows it to stay in the water column and allows the transport. To help answer these questions, helping with this, we sampled a hydrothermal plume that has one of the highest iron concentration we know of, which is the hydrothermal plume from the Rainbow hydrothermal vent field. We used the CTD sampler to sample 2 different stations, whereas station 2 is directly above the vent, and so our vent station, and station 3 is our off-vent station that we sampled a mile away from the actual source. And we started with looking at the bulk material of our samples. And there are different ways how we used or what we did to preserve the material. And one was using filters. And with these filters, we then went first to France, to Grenoble, to the synchrotron to measure XANTs. And here I'm only showing you the results from 2 different samples from both of these stations, the blue and the gray line. And you can see that they are very, very similar. You can also see in this plot the purple line, which is the iron edge of a synthetic ferrihydride. And you hope you agree that they are looking very similar to my samples. So based on this, I can say that most of the iron in my particles is already oxidized and has a very similar mineralogy to a ferrihydride. You can also see in this plot the yellow line, which is our indication for the reduced iron, and it's the iron edge of pyrite. And you can see marked with the orange line that my samples have this slight shift in direction of the iron 2 peak, which shows me that even though most of the iron is already oxidized, there seems to be a reduced iron part somewhere in my material. I also did some total particulate organic carbon measurements. And here it turns out that actually, yes, in the buoyant plume specifically, we have elevated concentration of organic carbon of up to 0.021 milligram per liter, which is significantly above the average concentration we have in the deep Atlantic seawater, which is usually around 0.007 milligram per liter, which is actually identical to what we measure in our off-vent station. And this is very nice because it fits to the overall idea that organic matter complexation stabilizes this iron. So yes, we have these higher concentrations. What I then did was looking at individual particles instead of the bulk material. And for this, I was using TEM, transmission electron microscopy. And most of the results you will see from now on are actually made with TEM. And these are made with the instruments I have here in Utrecht, which are also the instruments you have access to via the XIDE network. And you can see here 4 different examples from 4 different water depths from both of these stations. And you can see these little spherical iron colloids, which are aggregating together to forming these almost dendritic appearing structures. And you hope you agree that they were looking very, very similar. So whatever process potentially stabilizes the iron happens very early on. So we were really focusing on the deepest samples that we recovered directly above the vent, just a few seconds after mixing. And here it turns out that we actually have two different types of iron particles. On the top row, you can see an example that is very similar to the 4 examples I showed you before. And with selected area electron diffraction, we were able to show that this is actually a 2-line ferrihydride. So it's highly disordered. In the bottom column, you can see a second type, which is a little bit more compact. And it had almost these needle type of textures there. And this is actually a 6-line ferrihydride. So it's partly more ordered, but it's still not really crystalline. We then also looked at the chemistry of these particles using EDS, so energy dispersive spectroscopy. And here are maps of one specific example. And you can see that the iron and the phosphor is really in the center of this iron colloid. And then the chloride and the magnesium is a little bit more spread, and it's covering the whole colloid. We also recognized some silica, which is actually quite common in our samples. So they were often co-occurring with our iron particles. And then we had the first bigger surprise, which is that we actually don't have elevated concentration of carbon associated with our particles, which is surprising because this is one of the main theories how we can stabilize the iron particles. And we have this higher concentration in our bulk material, but apparently it's not associated with our particles. We then also did a few cross-sections about different particles. Here's an example of one of these 2-line ferrihydrides. And it turns out, if you're looking in the highlighted area with orange, that we have specific locations where we have a very high phosphor concentration. So overall, for this particle, we have a phosphor-iron ratio of 1:3, which is pretty high. And phosphor, of course, is very interesting because this is another essential micronutrient. Which means that we have a component consisting of phosphor and iron floating around the deep sea, would be like floating around of a candy for these microbes. So we wanted to know if these local occurrences are really of statistic relevance, and we can see it throughout our particle as well as over all of our samples, or if this is something that is very local and very rare. So to answer these questions, there would be 2 different options. We could either do a ton of these profile cross-sections above all of our particles, or what we actually decided to do is using a machine learning approach. And for this, I was using a software package called Sigma, which was developed within the Excite network, and it's freely available to use. And really simple what Sigma does, it is combining an autoencoder with a clustering model that automatically identifies distinct phases or so-called clusters in a hyperspectral data set. So very simple, it does 2 different things. So the first important step is training the neural network autoencoder. So it's using as an input these EDS elemental maps that we have from the particle, and then reducing it to just 2 dimensions. Because this EDS is a hyperspectral data set, because from every single pixel, we have the full spectra, so the full information about the elemental composition. But by reducing it to just 2 dimensions, we can just easily plot it in an XY scatter plot and then find different correlations. But keeping all of these informations, we also have in the individual maps. And then we're also using a decoder to bring it back to the original shape. So we actually know which pixel is located where in our particle. And during the training process, the software does it a couple of times to minimize the reconstruction loss. So the difference between our original data and the reconstructed data. And then if the reconstruction loss is minimized, we can actually use the trained autoencoder to create this latent space with our data. And then looks a little bit like this. The next step is what is happening is just a normal Gaussian mixture modeling. So just identifying clusters that are distinct from each other. And just a few more words on how to read these latent spaces. So if you would now have a pixel in the center of the latent space, that would mean that this pixel has a very similar signal compared to the overall signal that we have. And if the pixel is far away from the center, this means it's very, very different from the overall spectra. And also, if 2 pixels are far away from each other, this means they're very different from the signal. So how does it look with the particles. We're starting with this. So we have all these elemental information from our particle as well as the overall spectra. And then we let the software run with these data set, and you get something like this. So on the left side, you now can see the locations of the different clusters or phases. And then on the right side, you can see the correlating signal to this. So the software really nicely identified the silica. We already saw this pretty well in our EDS maps. And you can see on the right side, the software identified or summarized all the pixels that have a high silica peak. It also identifies these magnesium chloride as well as sulfur phase that is covering our particle, and identifies a phase that has a higher iron and phosphor concentration. So what we saw in just individual cross sections, we can actually observe this throughout the whole particle, and we're also able to observe these phase in almost all of our samples. And then, because we now have the signal for specifically this cluster or phase, we could quantify it. And it turns out there's actually a significant difference between the 2-line and the 6-line ferrihydride. So for the 2-line ferrihydride, we have a phosphor-iron ratio of 1:2, which is actually the maximum amount of phosphor which can be incorporated into the crystal structure of a ferrihydride. And then with the 6-line ferrihydride, we have a phosphor-iron ratio of 1:8, which is still actually pretty high, but it's significantly lower compared to the 2-line ferrihydride. Something else that was recognized by the software is a cluster enriched in iron, sulfur, and copper, which is very interesting for us because from the bulk observation, we already know that we have a reduced iron component, but so far we have only identified the oxidized iron in the ferrihydride. So now knowing that the software identified a phase that is enriched in these elements, we of course are super interested in figuring out what it is. And for this, I actually handed in an Excite proposal because we wanted to go back to the TM, but this time we want to do TM tomography, which means that you create a 3D reconstruction of your particle. And to do that, you have to tilt the stage to get images of all these different angles. And ferrihydride is you already saw it, highly disordered phase. So the contrast we see in our TM images is very low, which would mean if there would be a second phase that is crystalline, and we, by tilting the stage, align the axis, the crystal axis of this phase with the electron beam, we would get a really, really strong contrast and could immediately see if there's something hidden in our particle. So I went to the NanoLab and worked with the group, the Environmental Mineralogy Research Group from Dr. Michele Postfai, as well as their team, and they helped me to do the 3D reconstructions, as well as having very nice discussions with the whole team there. And then it turns out, so this is the result that I got. This is one 3D reconstruction of one of these 2-line ferrihydrides, and you can see these individual spherical iron colloids that are clustering together, forming these dendritic shape. And then it turns out that in the center, we actually have a fully crystalline second phase that is completely coated and covered by the ferrihydride. And because this is a fully crystalline phase, we could align the crystal axis of this phase with the electron beam and do really nice high-resolution images where we could actually identify lattice fringes, which you can see in the bottom row. And it was really amazing what they were able to do because this phase is still covered completely by the ferrihydride, but we got a very nice result at the end. And we also were able to get a diffraction pattern that we could index. So based on this, I know that the crystallography of this phase is very similar to a chalcopyrite. So in combination with the chemical information that we have, we now know that in the center of this oxidized iron ferrihydride is actually a chalcopyrite. And with this, I was able to create a little conceptual model on explaining, or that explains the early fate of the reduced iron in the first seconds and meters after venting. And right now we are arguing that the chalcopyrite already forms within the hydrothermal fluid, so before the actual venting of the fluid. But we have so much iron there that even though if all the sulfur and all the copper is bound with the iron, we still have a surplus of iron and we have some dissolved reduced iron. If this mixture is then venting and mixing with seawater, we have the fast oxidation of the iron as well as the formation of the ferrihydride. And right now we are arguing that, or in general, ferrihydrite forms via the clustering of so-called Keegan iron-13 clusters. And we are arguing that this clustering process occurs on the surface of the chalcopyrite. And this leads to these almost dendritic appearing structures. But we have so much extra iron there that they also do the clustering just by themselves, which creates this more compact ferrihydrite. And then over time, we have the adsorption of phosphate on the surface. And because the ferrihydrite that uses the chalcopyrite as a crystallization template has a more elongated shape, it has a bigger surface area. So the phosphate loading is much, much higher compared to the compact and dense ones, which actually leads to the fact that the compact ones with a lower phosphate loading is transforming into a more ordered 6-line ferrihydrite compared to the other dendritic appearing ferrihydrite with a high phosphate loading. Because phosphate adsorbed to the surface of a ferrihydrite leads to a dehydration of the surface, which limits the ability for dissolution and precipitation. So it limits the ability to transform from these highly disordered structure into a more ordered structure. And this is then what we see when we are sampling with our CTD sampler. We have this mixture of the compact 6-line ferrihydrite as well as the dendritic 2-line ferrihydrite that in part have these chalcopyrite cores. And this shows me that at least for rainbow, but potentially for other black smoker systems as well, the early preservation of these iron is not really controlled by organic complexation. It's more an inorganic process, specifically the coating of the iron 2 within the chalcopyrite by the oxidized iron of the ferrihydrite, which limits the oxidation of the chalcopyrite and preserves this and allows the transport into the deep sea. And with this, I will thank you very much for your attention, and I hope there is some time for a few questions.
Thank you, Lotta. Very interesting, and definitely there's still a lot of time left for questions. So please raise your hand so I know you would like to pose a question, or put it in the Suma Miadi Boza, please. Switch on your microphone. You can do it yourself and pose your question, please.
Yes. Yeah, hello. Thank you for the nice talk. Am I audible?
Yes, we can hear you. Yeah.
Thank you.
Please go ahead.
Actually, I'm working with some particles of an Archean precipitate, which is mainly I'm working on some BIF samples, which contains some jaspilite layers, and there I probably got some ferrihydrites like this, which are clustered together along with other mineral phases. So as you have described that these ferrihydrites are formed after the venting with a chalcopyrite core inside. So what if they got transported and they will precipitate at the ocean bottom, and what if they got modified to another phase, and what will be the fate of this chalcopyrite within them? Can you tell me?
That's a good question. So, of course, I'm hoping that a lot of this will actually be transported really far in the deep sea, and then potentially, I think at some point the chalcopyrite will oxidize. Even though it's slowed down by this coating, it will oxidize at some point. And then there's the question if it's still in the plume and still traveling, if this is just then absorbed by other phases or other microbes that are using that. So this is what I assume will happen in the water column, but of course some of them could also settle and will be then in the sediments. There also should be oxidizing, and then there's so much more organic there involved as well. So I'm not sure what will happen specifically with them, but I could imagine that this can be used by different microbes or organisms that are living there, but as well as just transforming into something like goethite or so over time. The only surprising thing is that we observed we also got a few sediment cores close to the rainbow hydrothermal vent field, as well as a little bit further away. We were also still able to see these ferrihydrites. We don't know if they also have these chalcopyrite cores, but we also saw this tendency to a reduced iron phase. So maybe there still is something. And if it's in the sediment and considering these really low sedimentation rates, which would mean they're extremely stable, but I'm not specifically working on the sediments cores there. But for me, as far as I know, it seems to be they're very, very stable, surprisingly.
Thank you so much. Thank you.
Okay, thanks for the question.
Thank you. So now we have Liana G. Penning. Please take the stage and pose your question. Oh, we
I
can't
can't hear you.
Oh, your microphone should be working.
Oh,
Oh, that's no. The system indicates that your microphone is on, but unfortunately we cannot hear you. Maybe you can write it down, your
okay, thank you.
question. That would be great. Yeah, thank you. Thank you,
Okay.
Liana. So I don't see any raised hands for this moment, but I have a question. So can this approach be used to study iron from other sources, such as dust and or rivers or any kind of other?
Yes, pretty sure. Also in part that is already done, that this is used. The big difference that we had in our samples, where we also get these really nice individual particles, is because of the second type of preservation we used. So I mentioned that for the bulk rocks, we were using the filters to preserve them, and this is a very conventional method. And a lot of people are using this, and you could do that on the surface waters to get more information about the dust that is coming down and the iron from this area, but also if you're closer to continents to sample there, the water column, and it's already done, people do this. The difference what we then did is this plunge freezing of some of the particles. And I think this was really a big step in improving the quality of the data set because we are minimizing all these preparation steps. So with the plunge freezing, what we do, we just immediately put some of the fluid on a TEM grid and then plunge freeze this. So we're not using the filters. We don't have to resuspend them to get them onto the TEM grid. So we're skipping a lot of preparation steps. And I think this is what makes a big difference in this specific study. And I'm pretty sure I would love to do it for more areas. I think it's a very cool method and it should be done more often. And I think it can really help us to understand better what is happening with these nanoparticles.
Would it then also mean that you would have like the particle, which is then, because you have less steps, that you will have it probably as much preserved as it was, and that would...
As pristine as possible. We're still using a CTD sampler. We still have to move it up on ship, where there will be some oxidation processes and alteration. So it's still not ideal. But yeah, I think it's already a big step forward on improving the method, how we are treating these samples.
Fantastic. And are there plans to scale up this research to other vent fields to maybe also get a bigger picture?
Ideally, yes. So first of all, I definitely would love to have more information about these naturally buoyant plume, because most of these really cool results are from the still buoyant plume directly above the venting. Doing this further away, because we also still know, so all these geotracer studies showed really nicely that we have reduced iron extremely far away. And just getting these samples and see if we find the same course would be super exciting just for rainbow itself, but of course also just comparing with different hydrothermal vent systems. Yeah, so I definitely would like to do that. I hope I have the chance to do that.
Yeah, that would be great. So there's it's 12:30, but we have time for one more question. So Sumyadeep, please pose your question.
Yeah, I have actually follow-up question to my previous one. So these ferrihydrides are stable in modern oceans, but can we expect them to be stable in Archean oceans where these atmospheric conditions were completely different?
This is something I just started discussing with a colleague. I never really considered that or was thinking about that because I'm so focused on current processes and what is happening right now. But this would be super interesting to dive deeper into and really think about what would happen with them if the chemistry of the oceans is so different. If we have less oxygen, for example, what happens then with the sulfide that is within the chalcopyrite? So I could imagine that we would have them, but what happens with them over the long run could be quite different compared to these days. So yeah, I just started discussing with a colleague about that because this, I think, could be a very interesting approach.
Yeah,
really
actually, I'm sorry to interrupt you. Actually,
No,
I'm
that's fine.
working with these samples where I got these ferrihydrides, and it's from Neo-Archean samples. So they are pretty much interesting, and I got some interesting clusters of pyrite instead of chalcopyrite within them. So I'm thinking about them, and I have also written a Excite project this year, which got selected actually.
Fantastic.
So
Congratulations.
I'm going to study them at Curtin, so under APT. So we are going to study the trace element concentrations there. Yeah, it's difficult, but I got wonderful preservation of these type of precipitates, and I got a huge number of layers where these ferrihydrides were stable. So actually, I'm now working with this stability field and how it got stable in that kind of atmospheric conditions. So yeah, that's all. Thank you.
That sounds very interesting.
Thank you for the input.
It's also impressive how stable they are. I'm still like, surprised by that.
Yeah, that is my question too.
That's cool. Thank you very much for the comment.
Yeah, thank you.
Very handy that they're so stable.
For measurements, yes.
Great. Okay, so unfortunately, I have not received the question from Liana Benning, but I will make sure that we will get that question and we will answer it.
I would love to.
Great. So it's 3 minutes past 12:30. Thank you very much for your attention, for being here at this webinar. We wish you a great summer, and we hope to see you again in September for the next webinar in this Excite Academy webinar series. So have a great day. Thank you.